Hello, greetings peeps. We're going to look at a problem involving gravity and free fall. And here's our situation. We have a tennis ball. It's launched vertically upwards from ground with a velocity of 25 meters per second. We want to find out a few things. A, how high does the tennis ball rise? How much time does it take to reach peak height for the tennis ball? How much time does it take to reach the ground from peak height? And what is its velocity just before hitting the ground? So these are all things that we can tackle with our equations of motion. We just have one added thing. We have to factor in this acceleration due to gravity. So the first thing I'm going to do is read it, and as I've done, and we're going to look at some of the key words. We have vertically upward, okay, and from ground. So we have somewhat of an origin there as well. Okay, so what I'm going to do is start with a drawing so we can understand what vertically upward means in context over here of a coordinate system. So we've got our tennis ball, and it's going to have some velocity known as v naught. Okay, it's got to have some initial velocity, original velocity upwards in order to get there in the first place. Something provided it. That something was some kind of force, but we'll look into forces sometime later. We just know that something is given it that initial original velocity. And this is 25 meters per second. And we know that this thing's going to go straight up and then reach its peak, and then it will fall down so that the v down here at the ground will be some value as well. So this is kind of after. I'm just going to draw this over here, v. And so we have before and after the launch. And what makes this significant over here is that we kind of need to analyze this in two parts because there's something special that happens at the very top. And here's what it is. At the top over here, the very top, v, I'll call peak, is 0 meters per second. It's that very moment where the object begins to reach its maximum height and then makes its return down. So the reason why that happens is because of the downward acceleration that is always downwards and always equal to 9.8 meters per second squared. All right? Thing is, what I want to do right now is also establish a coordinate system. Which way is positive, which way is negative? And I'm free to choose either one, but I'm going to, out of convention, choose positive to be up, right? We can call this the y-axis in some cases. And this downward direction is going to be negative. So if I'm going to follow that convention, because gravity, which is symbolized by g, it's so special, it's got its own letter, g. It's not a, it's g, right? It's going to be negative 9.8 meters per second squared because of the fact that it's pointing downwards. It's always pointing downwards. It's always 9.8 meters per second squared. Whether it's down here at its starting point, whether it's here at the top, anywhere in the middle, the acceleration due to gravity is the same. Down, 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 okay? In that direction. All right, and during the after, we can kind of call this our new v naught for when it hits the peak, and this velocity starts off at 0 meters per second, and then we'll accelerate downwards, downwards, until it hits the ground. All right, so that's our structure right now. What I'm going to do is set up some variables so that we can assign some values. Well, the thing is that we have g is negative 9.8 meters per second squared as a result of our coordinate system. We're given that v naught is positive 25 meters per second squared because it's heading upwards in the positive direction. And what else do we know? Well, not a whole lot, but we can fill in a few things. Because v peak over here is 0 meters per second, we can use that to our advantage and figure out, well, what the final, we know that final velocity anyway, if we consider our trip only upwards to its peak, and that's kind of what we need here for how high it rises. So v peak is 0 meters per second. Okay. And we don't know the height, which I'll call dy. And we don't know the time. But I'm sure we can find some equations to help us out. Well, let's just go with how high does it rise, all right? I'm given g, an acceleration, I'm given v naught, I'm given v peak. So what I'm going to do is find an equation that relates that to d, and the only one I can think of is v squared equals v naught squared plus 2ad, like that. All right, now I'm going to solve it for d, and then plug in the values afterwards, after we solve, right? But I can use an advantage here, knowing that v peak is 0, and that represents this v over here. That's where we start, the velocity of where we're going. So I'm free to do this, and now solve for d, okay? So we have negative v naught squared, I subtract it from both sides, equals 2ad, and therefore d equals negative v naught squared over 2a, and that'll give it to me. All right, so what is the value? Well, I'll plug in now. We have d equals negative 25 meters per second, and that thing is squared with a negative on the outside. We have 2 times, that's not a 9, that's an a, and actually I should say g, right? Because in this case, g, just bend the a little bit like that, is the special case here where we're looking at gravity. So I have 2 times negative 9.8 meters per second squared, like that. Notice that d becomes positive because I have the negative sign here and the negative sign here, and they will cancel out. So let's see what this value is. Da, da, da. So we got 25 squared, make sure to do that, divided by 2 times 9.8, 19.6. I get 31.9. Okay, 31.9 meters. So here we go. dy is 31.9 meters. All right, how much time did it take to get there? Now, I can use this result, or I may be able to find an equation that helps me get t another way. All right, let me just block this off for now. And I note that v equals v naught plus at has all that I need, noting that this guy over here, special acceleration of gravity, and that's g. Okay, well, v peak is 0, so I can do the same thing that I did before. I can say goodbye, baby. All right, and I can solve for t. So t equals negative v naught over g. Okay, and g is that negative 9.8 meters per second squared in this case due to our system over here. And so now I'm plugging the values, and we have negative 25 over negative 9.8. So we've got meters per second squared, like that, to give us seconds. And that is maybe about a little more than 2.5. Find out, 25 divided by 9.8, 2.55. It's pretty good. Okay, equals 2.55 seconds. Okay, so we have t equals 2.55 seconds. Let's box in that answer, and we'll box this one in too. How much time does it take to reach ground from peak height? Well, let's think about it. This is a symmetrical problem. Launching from ground, the heaven's supposed to be launched from ground, well, from a rocket, but we're going to call that our origin. So we'll pretend that that's from the ground, just to keep it simpler for symmetry's sake right now. We could later maybe get into some more complex situations, but we launch, goes up to peak, it comes down, it's going to go the same height because the acceleration is the same everywhere. The time at which it rises will be the same time that it takes to reach fall. We can actually prove that in the lab with some sensors. And I've got this wonderful clip with some NBA players where they're fitted with some sensors and stuff. And that's actually one of the things, the cool things that we find, that your time up is definitely the same as your time down. So without even doing any math, I can just use physics and reason this out with the logic. Okay, so how much time does it take? Guess what? It takes another 2.55 seconds to come down. Hey, all right. What's its velocity before hitting the ground? Okay. I can also use symmetry here. I don't even have to do any math for part D. Check this out. But I'm going to do the math just to prove it to you in a moment. But the up velocity is 25 meters per second. The down velocity just before hitting the ground at the same place has to be exactly the same due to symmetry. But the direction changes, so therefore it's negative. So we have this velocity here for the ground is equal to negative 25 meters per second. Okay, let's prove that out. I'm just going to wipe some of this away, but use some of this information so that we can see that that's true. All right, so what if we start off from peak where that particular V naught, if we just looked at the problem as a free fall problem from the very top, if we drop this 31.9 meters, what's the velocity going to be down here? So we can rephrase the problem like that. All right, so I'll just reset up the variables very quickly. Again, G is negative 9.8 meters per second squared, okay? And the V naught is 0 meters per second. And the dy is 31.9 meters. Since we're falling, we'll go with negative. That's our displacement. Because now I'm selecting the origin to be up here for this problem, and we're going down. But still considering the negative direction to be downward, like that. All right, so let's find the equation that gives us V, and guess what? It's this guy. V equals V naught squared plus 2AD. V squared equals V naught plus 2AD. And to simplify, V naught is 0. Okay, and what I have here is that V equals the square root of 2AD, and it's really dy because it's the vertical direction. No, not x, y. There we go. And all right. So what do I have? I have V equals square root of 2 times negative 9.8 meters per second squared times negative 31.9 meters, like that. Now, if I didn't take into account the negative over here, I would be taking the square root of a negative number, which is not so fun. We don't want any imaginary numbers in our physical world right now, so we're just going to be sure to have our signs correct. It's really, really important in physics that we do that. So, what do we got? 2 times 9.8, oops, 2 times 9.8 times 31.9 equals, and then the square root of that, I get 25.004, and like some rounding errors and stuff. Perfect. Okay, V equals 25 meters per second. Now we're going to understand that that's negative in the end, simply because, well, with the square root we can choose, remember, which value it is. So we have to consider the physics in this too, as well as the math. So we have negative 25 meters per second. You can't take a square root of a negative number, but when you take the square root of a number, you can decide whether or not it's positive or negative root. So it's the negative. V equals negative 25 meters per second, just like we had over here. We didn't have to do it this way, but we did, just to show it. And that's what it is. All right, we did a problem using gravity, our friend, 9.8 meters per second squared. And that's what it is. All right, Morad out.